The new Feersum NanoBeast will soon be upon us. It sits alongside the existing MicroBeast, and whilst it's very similar in many ways, it does have some distinctive features that differentiate it from the MicroBeast, so much so that it might prove useful to be able to tell them apart. Obviously, externally, they're quite visually distinctive. They're easy to tell apart, but how do we tell them apart from the inside? One way we can do that is to use the new device ID address in the latest firmware. Get this up. Okay, so device ID address FF04 is intended for precisely this purpose. If you read this address, read the byte, you'll get a 1 if you're running on a MicroBeast and a 2 when you're running on the new NanoBeast. Let me give you a quick demo of that using the world's greatest language, Forth. So all we're going to do is essentially the equivalent of a peak. Change my number base to hexadecimal. So in Forth we can peak a location by putting the address on the stack, FF04, and using the fetch operator, which is Forth's equivalent of a peak, and then the show operator, which will print out the result. So over here we've got a 2, and this is indeed my NanoBeast. All good so far. Let's do the same thing over here. So this is my MicroBeast on the right in red. I can do exactly the same thing, 0xFF04, fetch, show. By this time, I've got to do hex. There we go. 0xFF04, fetch, show. So this time I got 201, which is not what we expected. We just wanted the 1 bit, and this is because Forth, of course, deals in 16-bit quantities, cells as it calls it. So we can in fact use the byte-wide fetch operator, and now we get a 1. Just completeness sake, if I do a character fetch over here, I used the wrong location, FF04, let's start back to the 2. So far, so good. This all works nicely in 1.8 firmware, but that FF04 address isn't guaranteed not to move between firmware versions, and indeed it doesn't exist at all in firmwares prior to 1.8. I can show you that by running up BeastM, the MicroBeast emulator. It's wrong window, hold on, here it is. Get this guy running. I should have started it double size, but hopefully you can follow. We'll let this boot up. You can see 1.7 firmware. And I'll boot CPM. Where is it? Lower CPM. Format the RAM disk. New prompt. Things on our disk. So that's good. So let's halt this guy and have a look at that memory address. FF04. FF04 is where this little chevron mark is. You can see I've got a 2C in here. It's just meaningless. It's not the same thing on firmware prior to 1.8. Close that. Now, future versions of the BeastOS firmware might well get this kind of hardware detection built into the CPM get version BIOS call. But in the meantime, is there a more reliable technique that we can use? Well, of course there is. There's a specific technique that's sanctioned by Andy, so it's the approved way of doing things. And it all hinges around one of the differences between a MicroBeast and a NanoBeast, which is principally how the PIO works. So in a MicroBeast, you've got a classic Zilog Z80 PIO controller. It's actually the newer CMOS version of this chip, the Z84C20. But even these newer chips are becoming obsolete and increasingly difficult to find. So the NanoBeast doesn't have this chip. for exactly that reason, and it does instead, where's it gone, have its own CPLD, which does a lot of the glue logic, a bit like a ULA on a Spectrum, and the PIO functionality, or rather a sort of lightweight version of it, has been moved into this CPLD. I'm highlighting this, I think that's the CPLD, I'll check afterwards. So yes, so we have something that looks like a PIO port, or pair of PIO ports to most intents and purposes, but there are subtle differences, and this is the register map for the NanoBeast. This is the new register map, and you'll see that in the middle of our port A and port B registers, we've got these two new things called LCD translate low and LCD translate high, which are not there when you're dealing with a classic Z80PIO. So the classic Z80PIO has two ports. You can see this little diagram here, to make that a bit bigger. And each of these ports has a few registers, data in, data out, some control registers, and they're accessed in quite a weird way, much beloved way, but a weird way nevertheless. The interface is a little strange. NanoBeast, on the other hand, is much simpler. So basically, you've got data registers for both ports, and rather than a generic control register that's stateful and does various different things, like on the Z80PIO chip, one of the ports has a simple direction register, and the other port doesn't even have that. So you can see this in the new NanoBeast register mappings. So these are offsets from the Z80IO address space base, which is 0x10. You see we've got port A read write, port A direction, these two new LCD registers, and then we've got port B data, and that's all she wrote. So how we detect a NanoBeast hinges on this difference. So we're going to write a special value to these registers and read a special value back. It's deliberately designed to do that, to identify itself. And if we're running this code on a MicroBeast, we'll be writing to the port A control and port B control registers, which is mostly harmless, but not entirely harmless. There are some side effects that we'll have to deal with. So enough chatting, let's start doing some code and seeing how we can use this stuff. Okay, I'll be using Forth again, because as I mentioned, it is the greatest development environment known to man. I know some of you are traumatized by the built-in Forth editor, and Forth doesn't even have a crappy built-in Forth editor. But what we have got is Vi-like editor that we'll be using instead. So if I make a mistake, which is very likely indeed, then I won't have to retype all this stuff. So let's start a file, I'll call it whatbeast.fifth, like so, and I don't have vibe. I don't have vibe. Oh, okay, let's do it over here. Beast.forth. We'll do it on the MicroBeast, the red one. Here we go. So, going to write some Forth in here. Start with a comment. That's what a comment looks like. We'll define some constants for the ports on the MicroBeast, and we do that by putting in the value first and then saying we want a constant called MicroBeast port A data. Let's have another one. 0x12 constant MicroBeast port A control. Let's switch to port B, so that's 0x11 constant MicroBeast port B data. 0x13 finally constant MicroBeast port B control. Those are what those IO addresses mean on the MicroBeast, and let's have something similar. NanoBeast ports, and we'll call these 0x10 constant, but this time N for NanoBeast, port A data, 0x11 constant NanoBeast port A direction rather than control, and on port B we just have one data register. And that's all she wrote. I'm not going to define the LCD translation registers here. I'll just use the MicroBeast names for the same thing. So that's port A control and port B control. What else do we need? Oh, I mentioned that we write some special values to those LCD registers and we read some different special values back, and that's how we detect a NanoBeast. So let's define those constant, and we'll call them NanoBeast detection. And the magic value that we write is 4F. And in the firmware, this is called NIO test bits. So we'll use the same name, might as well. And the value we get back from the lower register is D4. And that's called NIO valid lower. And the value we get back from the other side, OXFA, NIO valid, can you guess? Mobile. Good. Okay, so those are all the constants we need. Probably going to define a couple more actually while I'm at it, and I'll call those MicroBeast restore. But don't worry about these too much, I'll talk about them when I come to use them. Mode and FF. We'll call this mask. Okay, brilliant. So what can we do with these constants? Well, let's make ourselves a custom word to peek and poke our way to glory. A word in Forth, it's what Forth calls a procedure or a function, subroutine, if you want to call it. Forth calls them words. So we're going to call our new word is NanoBeast. So this is a word that you run and it will return true if it's running on a NanoBeast, false if it isn't. And what are we going to do with our new word? We're going to take the NIO test bits value and take a MicroBeast port A control register address, and we're going to do an out, like a Z80 out or a Spectrum Basic out. It's an out to the IO bus, and we're going to do the same thing this time to the B control register, another out. There we go. Once we've done our outs, we are going to follow them up with a couple of ins. So MA control address again, and this time we'll just go in. So when I do an in, what's happening here is this MA control pushes this address onto the stack, and in consumes that value from the stack and pushes to the stack the contents of that IO address. So it swaps the address for the contents on top of the stack. I'm going to push another value to the top of the stack, which is NIO valid lower, which is the value I want to get. So this puts on the stack the value that actually exists in the hardware, and this adds to the top of the stack the value I'd expect if I'm running on a NanoBeast. So I've got two values on the top of the stack, and I can compare them with an equals. So if they're equal, now I'll just have a true on the top of the stack, and if they're not, I'll have a false on the top of the stack. So now I've got a true or a false depending on whether the lower byte was valid, and we can do exactly the same thing again for the B register and compare it with the NIO valid upper and do an equal. So now I've got one true on the stack depending on whether the lower byte was valid, and another true or false depending on whether the upper byte was valid. So I need both of those to be true, and the best way to return a true if two other things are true is to AND them together, to use the AND logical operation. So now I'll only have true on the stack if both of those registers match the values I was expecting, and that means we're running on a NanoBeast. And then finally, one last bit of housekeeping. I mentioned that we're writing to the MicroBeast's port A control registers and port B control registers. So if we're actually running on a MicroBeast, not on a NanoBeast, then what we've done is overwrite what was in those control registers, which is not ideal. The A port is entirely for users' own use. So it's not used by the firmware or the operating system at all. So that doesn't matter so much, because you could argue, well, we should know what goes in that register so we can restore it at will. But the other port B, is used for some system services. So things like the I2C interface runs on port B, and various system interrupts. I think the real-time clock interrupt, the UART interrupt and the backplane interrupt all come in through port B. So by overwriting port B control register, we are going to cause havoc and mayhem. So we need to restore the correct value when we've finished doing this MicroBeast NanoBeast test. Only problem is these control registers for port A and port B are write only. We can't read them. If we attempt to read those I/O addresses, we'll just get back garbage. And even if we could read them, it wouldn't really help us, because like I said, they can be sequential. They're backed by a little state machine, and it expects 2, sometimes 3 consecutive writes, one after the other, and it doesn't respond to reads in that way at all. So this presents us with a bit of a problem, and the only way around it really is to use our a priori knowledge of what was in those registers before we started messing around with them, which we can get by, you know, trawling through the MicroBeast source code, firmware source code, and seeing what those values were. And that's what these 2 restore values that I typed in and glossed over earlier are going to be for. So what we're actually going to do is just say MicroBeast port B mode, MicroBeast port B control out. So I'm going to write this value OXCF to, that's not how you spell out, to the port B control register. So that sets up the I/O mode for that port, and then it's one of these sequential things. Masks, and now we need to write an I/O mask to MB control again, so it's the same address, but the second write does something different, and this is telling it which bits are inputs and which bits are outputs. So this will make sure that our interrupts continue to work. When we're done with all that, we can finish our word. That's the end of our definition. I'm going to add one more simple word, which is basically just to make it a bit prettier to use. So what we're going to do here is call our NanoBeast word. So now we've got a true on top of the stack if we're running on a NanoBeast, and a false if we're not. So if it's true, then we're going to print a string, which is .quote in fourth, and we're going to print out NanoBeast. If it wasn't true, else, we're going to print out MicroBeast. And we're going to use a then to finish that clause, carriage return, just to move the cursor down the line and end our definition. And that is all we need. So let's try it out on the MicroBeast. Start up and forth. And include, what did I call it? Beast. But forth. Good. And let's run our function, or what? Sorry, our word on what beast word. It's a MicroBeast. Brilliant. It's exactly what we wanted. We have got ant4th over here, but I don't have that file that I just made. So what I can do is use a little bit of beast tty. That's this terminal emulator. A little bit of beast tty magic to copy it over. So if I do dir here and find the file that I just wrote, whatbeast.forth, there we go. Grab that, drop it over here, copy, send. There we go, we should have whatbeast.forth over here. We do, excellent. So fire up and forth. Let's include whatbeast.forth. Type whatbeast. There we are. Over here we're a NanoBeast, and over here we're a MicroBeast, and our MicroBeast continues to work, so it's a good sign that we've effectively reset the registers, or restored the registers correctly. me from the future here. I glibly said that we'd restored everything and that our interrupts were working properly without actually confirming that was the case. So let's quickly come back and do that. I've already run whatbeast, so we've done our poking. Now I can do ticks to fetch the system timer value, which is updated by the firmware every time it gets an interrupt from the real-time clock. So if this value doesn't change, then we're broken interrupts. Ticks is a 32-bit value, 2 cells, so we need to do, can't use a regular dot, we need a D dot to print out the value of ticks. So we go 3559, let's wait a little bit, type slowly, so some time can pass, run it again, 4059, time is ticking, all is well.